Okay, we're starting the new unit of system of equations. Now, this unit is part of relations and functions, that outcome, general outcome, and it relies a lot on the knowledge of equations of lines, which you just finished. So it's not like you can just forget about the last unit. It's certainly going to help you to be able to remember how to graph a linear equation, etc. But there will be more algebraic work that we'll be doing in this unit. So let's take a look at an example of a case where we might want to use a system of equations, and then we'll talk about what a system is. So it says a cage at the Calgary Zoo contains only flamingos and zebras with a total of 30 eyes and 44 feet. Assuming that there are no deformities, missing parts, or extra parts on the flamingos or zebras, how many of each animal do you think there are in the cage? So you can do some guesses and checks and see what you think. But really, we want a method of finding out exactly. So you know that there's 2 eyes for a flamingo and 2 for a zebra. But for a zebra, there's 4 feet, and for a flamingo, only 2. So that's why you can't just divide them, right? So we can use a model involving a system of equations that would allow us to verify our answer by the question above. Let F be the number of flamingos, Z be the number of zebras. Write 2 equations that model it. Well, so for a flamingo, they have 2 eyes, so that'll be 2 times F. And for a zebra, they have 2 eyes, so 2Z. And the total number of eyes is 30. Then for feet, for a flamingo, 2 feet. 2 times the number of flamingos gives the number of feet for flamingos. And then 4 times the number of zebras, and that's going to be 44. Okay, so that's for the eyes here, and this is for the feet. And use the equations to verify your answer. So maybe if we looked back up here, we actually didn't do it. So if we were to look here, maybe we would think there are 15 and 15. Okay, now if we did that, we can tell, oh, sorry, not 15. Let's do 8 and 7. So let's say 8 and 7, then the total, that would satisfy the eyes part. But then let's check here. So this is how we would verify. So the left side and the right side of this second equation, you go 2 times the flamingos plus 4 times the number of zebras, and see if we get 44. So that's 16 plus 28, and that's 44. So my random guess was actually quite accurate. It was exactly accurate. So that's how many there will be. But that was a guess. So I could have said, okay, I could have said 10 flamingos, that's 20 eyes, and 5 zebras, that would be 30 in total. But then if I put that in, 2 times 10 is 20, 4 times 5 is 20, and that would be only 40 feet, so that wouldn't work. So when taken together, the 2 equations relating the number of flamingos and zebras with the number of eyes and feet is an example of a system of equations. So a system is a set of equations that are considered together. In this unit, we will work with systems of 2 linear equations. A solution to a system of 2 equations is a pair of values that satisfy both. Okay, an ordered pair or 2 values written separately. So here's another one. A school district has small buses that carry 12 passengers, large buses that carry 24. The total passenger capacity for all the buses is 780. There are 20 more small buses than large. What unknowns do we want to find? Define variables for those unknown values. So often in a question, it will tell you the very last sentence will be what you're asked to find. But here, we want to know how many small buses there are and how many large buses. So we'll let S be the number of small buses, and we'll let L be the number of large buses. And so the system will be, so the total passenger capacity is 780. Well, for each small bus, it carries 12 passengers. So 12 times the number of small buses plus 24 times the number of large buses will give us the total of all passengers. Then it says there are 20 more small buses than large buses. Okay, so our small buses is S. That's equal to the large plus 20, because there's 20 more small than the large. So we have to add, that's one way of showing it. You could subtract them to get 20. In any case, that is the system. Then you're told that there are 35 small buses and 15 large buses. Use the system to verify. So we have to check in both equations. So I'm going to call that equation 1 and that equation 2. And I always set it up as what I call a T-chart to keep the equations, the left side and right side, separate, because we don't know for sure if it works. So 35 small buses and 15 large. The right side says 780. So now we multiply 12 times 35. So that's 420 plus 24 times 15 is 360. Add those together, we get 780. So the left side equals the right side. So that works for the first equation, but we do need to check the second equation. So the small buses was 35. The large buses, 15 plus 20 is 35. So left side equals right side. So yes, that is the number of buses. Okay, next one, a school raised $195 by collecting 3,000 items for recycling. The school received 5 cents for each pop can and 20 cents for each large bottle. What unknowns do we want to find? Define variables for those. Again, in a lot of questions, they will ask what to find, and so that's your hint of what your unknowns are. So basically the recyclables are the pop cans and the large bottles. And so we want to know, we already know the value we get. We want to know how many of them. So let's let P be the number of pop cans. And we don't just say let P be pop cans. We need to describe what we're looking, the number of them. Because you could, if you said P be pop cans, maybe you think it's the price of them or the recycling fee or whatever. So it's the number of them. Let L be the number of large bottles. Okay, so create a system. So 3,000 items were collected. So that means P plus L is 3,000. Then we want to look at the money. So this is in dollars and these are in cents. So I'm going to convert these to cents. So 5 cents is in dollars 0.05. 20 cents is in dollars 0.20. So now we're going to have 0.05p plus 0.20L equals 195. Then it gives us a possible answer. 2,700 pop cans, 300 large. Use the linear system to verify these numbers. So we want to do first equation, second equation. And so we'll have 2,700 plus 300. Right side is 3,000. That's pretty obvious. It does work. And the next one, equation 0.05 times 2,700 plus 0.2 times 300. And the right side is 195. So 0.05 times 2,700 is 135. 0.2 times 300 is 60. And yeah, it works. Okay. So then turn over the page to the next. Okay, so this next example gives the equations. All right, so it says a store sells wheels for roller skates in packages of 4 and wheels for inline skates in packages of 8. A situation about wheels was modeled by the linear system. So modeling equations that model something means it represents the situation using variables. So the two equations are up there. Explain the meaning of each variable. What do you think I represents? What do you think R represents? So sometimes we use letters that kind of represent the situation. But do you think I is the cost of inline skates or wheels? What do you think? Yes or no? Yes, thumbs up.
Oh, sure.
Do you think it represents the cost? Thumbs up or thumbs down? Down or up? Down, right? Not to do with the cost. A situation was modeled because take a look, we aren't given any information about the cost. It says I plus R equals 80, and then it says 8I plus 4R equals 440. Well, we're told in the first sentence that packages for roller skates, the wheels come in packages of 4. And notice how it's 4R here, right? So that means R must be the number of packages of wheels of roller skates. So R is the number of packages of roller skate wheels. And then I is in for inline skates, packages of 8 wheels. So I is the number of packages, PKGS is my short form for packages, of inline skate wheels. Okay, so write a problem that is modeled by this. So basically, these equations tell us. So our problem would be the number of packages of wheels is 80. Okay. The total number of wheels is 440. Okay. How many packages of each type of wheel were sold? Okay. Because obviously if I plus R is 80, you could have 75 inline plus 4 roller skate packages, but that doesn't mean that that would be 440 wheels. Okay, we're not going to solve that in this lesson. That's in future lessons. Later today we'll do some graphically in order to get the right combo that works, basically. So the next one says a hot dog stand sells 3 hot dogs and 5 drinks for $21. 4 drinks and 6 hot dogs costs $24. Is the system of linear equations shown correct? If not, fix it. And what do the variables represent? So take a look. I see 3h and 5d equals 21. So that seems right or correct for that first statement. And that would mean that, remember, 21 is the price, and it says 5 drinks. So D must be the price of a drink, and H is the price of a hot dog. So let H be the price of a hot dog. Let D be the price of a drink. Don't just go H is hot dog. That doesn't mean anything. Okay, it's not the number of hot dogs. Okay, we're told the number. Okay, H is not hot dog. H is the price of a hot dog. Okay. So then take a look for the next one. 4 drinks and 6. So we've got 4 and 6, but notice how the 4 is with the H. So this is incorrect. Okay, this should be 4D plus 6H equals 24. Okay. So the numbers were just mixed up with the variables in that one. Okay, so when you have a system of equations, the solution you get has to satisfy both equations in order to be a solution. So remember, each of these is an equation of a line. So you would have 2 lines, okay, and a point here satisfies, if that's line A and this is line B, that point there satisfies line A. It makes the equation true. But that point is not on line B, so it would not satisfy line B. The point that you want is this point here, because it's on both line A and line B. So when we check here, we want to see if the point -10, 1 is on both of those lines. So the proper way of doing this is to show, basically to show each equation separated into the left side and the right side. So I call them T charts because it looks like a T. So a big T and a big T. Then I call this left side LS and right side. And this is for equation 1, which I'm going to label that as equation 1, and this is equation 2. So this is equation 2, left side, right side. Okay, so then in equation 1, we're going to, this is your X value, and this is your Y value. So you're going to replace X with -10 and Y with 1. I'm just going to move this line over a little bit here. Okay, the right side is negative 13. And you might think, oh, why can't I just put it in with an equal sign? Just substitute it in. Because that point might not satisfy the equation. So then you're saying something is equal when it's not equal. By separating it with that vertical line, then there's no worry about that. So that's negative 20 plus 7, which is negative 13. So in this case, it is, so that's true. So the left side equals the right side. Okay. Then we'll do the same thing. I'm just going to move my line over a little bit here. Yes. Yeah, you should show your steps. Yeah. And then if it asks you to verify, like in a written response, but if you're just verifying for yourself, you don't have to. For the right hand, for the equation 2, my left side is negative bracket, negative 10 plus bracket 1. So I put brackets around whatever I'm substituting. My right side is 9. So when I do this, I get 10 plus 1, which is 11. So the left side is not equal to the right side. So this is not a solution. Okay, so negative 10, 1 is not a solution. I'll just maybe. That's my abbreviation for solution, SOL apostrophe N. So what? SOL apostrophe N is my abbreviation for solution. Oh, it's not a solution. Okay, so same thing we're going to check in the next one. So my first equation, my second equation. So now my x value of negative 10 goes on the left. On my right, 3 times 1 minus 13. So that's going to be 3 minus 13, which is negative 10. So that works. Okay, and then we'll do the same for the second equation. So the y is 1 minus 2 times negative 10. The right side is 21. Okay, so 1 plus 20 is 21. So the left side equals the right side in this case. So that point works for both of them. So that means it is a solution. Okay, so therefore, negative 10, 1 is a solution to the system. Guys. Well, good. Just keep your mouth quiet. Good, then keep your mouth quiet. I don't care whether you've done it or not. Okay, so take a look at the next one. Is the system, so it's 2 equations. So a system is 2 or more equations. That's what a system is. So in grade 10, we're sticking to 2. Grade 11, we're sticking to 2. Grade 12, maybe to 3 in the odd situation. And then if you go on in math, you'll do more. But in this case, it is 2. But take a look. This says a linear system. Are both of those linear equations? Look on your paper. Okay. So, do you see a square? Yes, that is not linear. Remember, linear is degree 1. So this is not linear. So therefore, not a linear system. Okay, for a linear system, both of them have to be linear. That makes sense, right? Okay, so you can do the practice in a bit. We want to get into the graphing. Okay. So turn over to the graphing. I'm just going to